So let's take a look at the next problem. The dice in the car as it accelerates along. So you have a car. And we know how dice hang. They hang vertically. Why? Well, because gravity's pulling them down, tension's pulling them up. We're in equilibrium. Ah, but this is not in equilibrium. We're accelerating forward, right? And so we know the dice swing back like that. Okay, and now the dice are here. And that makes sense because in order to accelerate forward, the tension has to have a horizontal component. Okay? And so, you know, let's take a look at the dice because that's where all the action's really going on. Maybe I make this a little bigger. What do we got? We got M naught. And we got some tension pulling at this 20 degrees. Okay. And we can label these. Here's the tension. And here's the force of gravity. Right, so now I have these two forces, and what do I do with them? And I realize, oh, you know, the most important thing I don't put here, and that is I know the vector sum of the forces must equal mass times acceleration. But I don't know how to add these because I don't know how big tension is. So, for instance, if I wanted to add them, like vectors, I should. I've got the force of gravity pulling down. And I've got the tension, you know, pulling in some direction. But I don't know how big the tension is. And so one of the very important things we need to remember is ask ourselves, what the hell's going on? This thing's accelerating. And what's the direction of acceleration? The acceleration is horizontal, right? The car is accelerating in this direction, not this direction or that direction. Right? So we recognize that acceleration is in this direction. The vector sum of the forces, or the resultant force, must also be in this direction. So here's force of gravity plus tension. Well, the sum of those two guys better be in this direction. So this must be the resultant force, which is, of course, the same as the vector sum of the forces. So I made this guy too big. And this is, you know, this is the tension here pulling on it. And this is a vector sum of the forces. And this is a 20-degree angle, because the direction of the string is the same as the direction of its tension. Okay? So now we can find the acceleration, because the acceleration is just equal to the force over the mass and the resultant force over the mass, the total force. So we need to find what this guy is. So we have an angle. This is a right angle, because that's down and that's horizontal. And I can say, oh, looks like a tangent. Tangent of 20 is equal to opposite over adjacent, force of gravity over the resultant force. And then the resultant force is just equal the force of gravity divided by tangent of 20. Okay? And so we're glad we didn't put any numbers in, because now I've got the force of gravity over mass times tangent 20. Right, but the force of gravity is just mg over m tan 20. Oops, sorry. And the masses cancel, so the acceleration is equal to g divided by the tangent of 20. Okay? Now, how am I going to get that number? I'm going to need a calculator, but Pete doesn't let us use calculators on a test. And we shouldn't use them for homework, he says, except mastering physics. Right? Well, let's take a look. First of all, I could just look at this triangle, right? Did I make this about 20 degrees? Maybe not. Maybe that's a little bit bigger than 20 degrees. But it'd be pretty good if I just left it there. I would say 20 degrees is a little bit less, right? Like this. Okay? So there's your tension. And so this is a force of gravity. So then how big is the resultant force? Well, that's 1 times gravity, 2 times gravity, about 3 times gravity, I'd say. So the resultant force is about 3 times gravity, and then you divide by mass and you get an acceleration of 3 gravities. Well, that's as Elliot said, that's hauling ass, I believe, right? So that would be about 3 gravities. 3 times gravity, or about 30 meters per second squared. And then ask yourself, can you do that? I mean, if I drop you off a cliff, you accelerate at 10 meters per second squared. So we're accelerating at 3 times that. And what kind of coefficient of friction would you need for this? And what you find, of course, is if you have a car, and we know that gravity's pulling down, and we're in equilibrium, some of the forces in the y direction are equal to 0, right? So that the normal force pushing up must be equal to the same, okay? Then the force in the y direction is caused by friction, right? You have the wheels here. The wheels are pushing backwards on the road, and you can notice that if there's some rocks, they get shot back. And that force of friction is what pushes us forward. So the force of friction is the only force in the x direction, must equal mass times acceleration. And you're telling me that's mass times 3 gravities, or 30 meters per second squared. Well, that force of friction is just mu times the normal force, which you're telling me is mu times mg. And so what we realize is mg cancels on both these sides, and mu is equal to 3. That means if you have a normal force of 1 Newton, it gives you a frictional force of 3 newtons sideways. Is that possible? Right. Well, there are a lot of substances that is possible, and it's difficult, but you can get it in some tires, not your regular tires, which are maybe mu of 1. But in dragster tires, they can. If you notice, if you've ever watched a movie of dragsters, they burn out at the starting line as they warm up, and they leave a layer of hot, clean rubber, very sticky rubber, at the starting line. And then they back up over it, and then they take off, and they have hot rubber on the tire and hot rubber on the ground, and it sticks. And so that's how they can get that very high coefficient of friction, and they can get really good accelerations. And their dice, if they had them on the window, might be hanging back at 20 degrees.